Okay, so today I will be discussing gravitational potential. And to start, let's look at a very simple example. So let's say we have a box of mass m on some height that gives us the gravitational potential energy of 0. So its height will be 0. So now we move it up, we exert some force on it and we move it up so that it is at height h. And now we have to find what is the final gravitational potential energy. Now remember that the change in energy is actually the work done on an object. And the work done on an object is force dot d. So what force do we have to counteract to move this box up to some height h? Well, we have to counteract the force of gravity, which is mg. So we know that since we're not going to be dealing with kinetic energy here, we can just say that V final is equal to 0 and V initial is equal to 0. So the only change that occurs is the change in gravitational energy. So we know then that work equals force times distance, and this is actually a dot product because these are vector quantities. But since the force that we will exert to move this up is in the same direction as the movement of the box, right? So the dot product equals ft cosine theta, but we know that theta is equal to 0 because the force we exert is up and the distance it moves is also up, so it's 0. So this is 0, so this is all 1. So force dot d just equals to force times distance. So we know that work will equals mg, and then the distance we move it up, which is h. So from this equation we can tell that the initial gravitational energy is 0, and the final gravitational energy would be the total work done, which is mgh. So from this equation we can say that the gravitational energy at any given point is mgh. And h is of course the difference from the 0 potential, where the gravitational potential is 0, to some height h, right? Okay, now let's look at a slightly different version of this problem. Let's say that we have a box at some height h and we drop it so that it lands downwards. Right, this is h. And we can say that since we know from this problem over here that the initial gravitational energy is mgh, we can say that this height is 0, so the final gravitational energy is also 0, and we can say that initial velocity is 0. So what is the final velocity? Well, we know that the total mechanical energy change is equal to 0. So the initial quantities, so the total mechanical energy at this point over here will equal the total mechanical energy at this point over here. So at this point over here, I'll label this as the energy initial, is equals to the gravitational, right? Energy is equal to kinetic energy plus gravitational energy. So in this is the kinetic energy is 0 because the velocity is 0, so 1/2 mv squared goes to 0, and then plus the gravitational energy, which is mgh. And the final energy will be, actually, we know that there is some final velocity, so 1/2 mv final squared, but then we know that the gravitational energy is 0 because h is 0, so this would be 0. So we know that E initial equals to ET because their energy, the difference between them is 0. So we know that mgh will equal to 1/2 mv final squared. So from this equation we can determine the v final, which would be 2gh, the square root of that, right? So I'll tie this back later on when we discuss something more difficult. So now let's focus on, let's say we have some planet with mass m, and at radius r1, it has a satellite, right? So this is a circular orbit. Doesn't look like much of a circle, but let's pretend it is. So a circular orbit, and this is a satellite with mass m. So remember that the force done by the planet on this satellite would be force gravity equals, and here we use the general equation, and the general equation is gm times the mass of the planet times the mass of the satellite over r squared. Okay, so now let's say we want to move the satellite to some r2. So of course the gravitational potential energy has to change, right? And let's remember that the gravitational potential energy at this point is equal to this point, because this line that I drew over here, this circle, is the same, has the same gravitational potential, right? Okay, so now let's say, so now we have to determine the work we have to do to move this satellite from R1 to R2. So work is equals to the integral from, and we are moving it from R1 to R2 of the force gravity times the distance, right, times dr, the distance over here. So when we plug this equation in, we get R1, R2, r squared. And actually the top part I could have pulled out because they're constants, and dr. And so when I solve for this integral, I get that the work done on the satellite to get it out of R1 and into R2 would be the constant times the masses over 1. Oh, negative, right? Negative, because this is R2, so it would be times -1. R2 minus 1 over R1, right? Okay, so now we know that the work done was actually the change in gravitational energy, which would be U2 minus U1. So now we know that the gravitational energy in this form is written as negative Gm times small m over r. This is the gravitational potential energy of a satellite far away from a planet. So now, like we looked in this problem at the final velocity, I want to discuss the escape velocity. But first, we have to determine the total energy at this point versus this point. So let's say that this will be the initial condition. So the total mechanical energy initial will have to be, again, the gravitational energy plus the kinetic energy. So it would be 1/2 mb, let's say 1 squared. Let's say at this point the velocity is v1, and at this point it's v2. Okay, so plus, oh, this is the kinetic energy, and the gravitational energy would be negative Gm over r1. And the second one, the final one, would be 1/2 mv2 squared minus or plus negative Gm r2. Alright, so now we need to determine the escape velocity. Okay, well, before that, we know that E initial equals E final, so the change in the total energy is 0. So we can plug in that at any given, if at any given point, at any given radius, the kinetic energy plus potential energy will always be equal to the other point, so R1. So the total mechanical energy does not change depending on the radius you have, right? So these are equals. Okay, so now let's say that we need to find the escape velocity. So for V1, we will substitute the escape velocity. And for R1, we will substitute the radius of this planet, right? Because that's where it will be starting off. So R1 will actually be the radius of the planet. But what would be our final velocity? Well, let's look at the radius first. The radius, right, where the gravitational potential energy will be 0, that would be R2 would equal 0, right? Because in this case, then at some distance very far, I mean infinity, right? Infinity. At some distance very far away, infinity, the gravitational potential will be 0. So by that time, V2 can be 0 too, right? So because by that time all the work, the velocity has been decreasing because it has been feeling the gravitational potential pull, right, on it. So but now since it escaped, the velocity can be 0 because we want to know the minimum escape velocity. So now we went from our planet to infinity. So we can say that 1/2 mv escape squared minus gmm of r will equal to 1/2 mv2 squared, which is 0, so this will be 0, plus negative gmmr2, which is infinity, right? This is infinity, so this whole thing would be 0, because any number divided by infinity is 0, right? It becomes infinitesimally small. In reality, this will never be 0, but for this purpose it serves just as well. So then when we get this, we get that this side is 0, so 1/2 mv escape velocity squared will have to equal gm, both of the masses, over r. So the escape velocity in this case will equal to 2g big M over r square root. And now an interesting thing is that neither this equation nor this equation, they don't have the object's mass in them. So object's mass is irrelevant, right? Alright, so that's about it. So also worth noting that because of this, the gravitational potential energy is actually conservationalist energy. And that's all for it's a conservative force, and that's all for today. Okay.